Hi, this is Parisa, and we are doing just A7, assignment 7 of the AI DQ networks. And the environment we're using is cart pole, is this one that there's a cart moving. Left and right are the possible actions, and the goal is for the pole not to fall like this. And to do so, we're importing the packages. The environment is called cart pole dash v1 from gym, and we had this before. These are the possible actions, and the observations include positions and velocity of the cart and pole angle and the velocity at the tip. And we can take a step to move and change the state, and dawn shows is a flag that shows if the episode is terminated or not. To test it, we take a random action by inf.actionspace.sample and reset the environment. So we take a step with a random action to see observation, reward, done, and info. Here, the random action is 1 pushing toward right, and these are the observed values, the reward and done. And oh, I forgot to say reward as 1 whenever as for each time step the uh, the pole doesn't fall, the reward is positive 1. So here it doesn't fall, so it's 1. And so here we can see the limitations of position won't go beyond -4 from left and 4 from right, and the speed doesn't go any faster than 3.4 in either direction, and so on and so forth. And we have the epsilon greedy action selection function for the exploration rate, that the random number we generate uniformly between 0 and 1 for each of them that is smaller than the exploration rate. We do explore by taking the random action. Otherwise, we take the best possible action. So other inputs are observation and DQN agent. We can predict the possible actions by giving the current observation to the agent dot predict, and the argmax will give us the best option. Okay, the next function that we need to define, so it's the replay function. It takes the target agent and the DQN agent, and the goal is so the target q value is equal to reward as we had before, plus the a discounted value of the best possible action in the next the q value of the best possible action in the next state. And the goal is to minimize the difference between this target q value and the DQN agent q value. So this is delta, the difference between these two values. We want to minimize it. And so here is where we define the replay function. It takes in the memory that keeps track of the things that change along the time. We will discuss this later. The DQI agent, the target agent, the batch size, and that discount factor is called gamma. States batch and the Q value batch in the beginning are empty, and mini batch is selected randomly from the memory given the batch size. Um, and for this mini batch, for each mini batch, so mini batch is a random sample from the memory, and this can tell us what is restored in the memory. It includes current observation, action, reward, observation next, and done. So we are keeping track, the memory keeps track of all of these values at a time. And for each of these in the sample mini batch that we have, we check in the beginning if it's not done, if the episode is not terminated, The target is calculated given the equation we had up there, reward plus gamma times argmax of the agent target agent that predict of the observation next. Otherwise, the target is only equal to reward if it's done. And so here the DQ agent outputs Q values for all the actions. Um, so it gets current observation, and by that it gets current Q, and current Q um, of the the so action is loaded from the memory from the mini batch. Current Q of that action gets equal to target. So it updates the Q value for the action that was taken here. So the next step is to update the states batch by adding the current observation to the list, and the Q values batch that we add current Q to it. And when the loop is finished, we have an array of state batches, different state batches along the entire mini batch, and all different Q values, Q value batch for the entire mini batch. And here we are training the DQ agent by fit function. Give it the state batch and Q value batch, a number of epochs, and a variable shows how it is displayed. The output is displayed. So if it's 0, it's not displaying much. I have run this before, so maybe it's better not to run, so that we don't need to wait. Um, And at the end, it returns this DQ agent that has been fed with um, these parameters. So we're initiating some initial values like maximum number of episodes, the value of gamma, the discount factor, memory, and target update steps. Then the environment variables include number of actions, that are 2, and number of observations. And batch size is selected as 64, learning rate as a small value, and the optimizer is Atom. The next exercise is that our DQN agent uses a neural network that is defined here. It has 4 layers of dense layers, and then takes the observation as input and output an action for the agent to execute. So here we define that the QA agent is a sequential network. In the beginning, we add a dense layer of 64 filters, and in the first layer, we give the input dimension to it. That is the number of observations with the activation of ReLU. Following layers are dense with different filters. The number of filters in the first one is 64, and the second one is 24. And in the hidden layers, and we don't need to define the input dimension anymore, because it's automatically can be determined from the previous layers. And the last layer finally takes in a number of actions and the activation. So it's a dense layer that gives us 2 outputs for the 2 actions. It selects the action for us with linear activation. Oh, it asks why we have the output has 2 dimensions, because we have 2 actions and we want to output the actions. So we won't have any output other than the 2 possible actions, and we want our network to just have 2 actions, 2 outputs. Then we need to compile, defining the loss as mean square error and the optimizer as Atom, given the learning rate defined up there. And we can see the summary here, number of parameters that in each layer you can see, and the combined number of parameters for the entire network, and a few other initialization. The starting epsilon is 1, to get the best out of exploration. And as the time passes, the decay rate is 0.95, and the minimum value for epsilon 0.05, to minimize the exploration rate when it has already explored enough. The next exercise will ask us to select the action using select action function that we defined up there, and take a step in the environment, and then gather experience. To do so we are doing the main training loop. We update the update counter value 0, and every time it counts, it's added by 1. And the rewards for now is empty, and it will get filled as the time passes. The target agent initially is the DQ agent, but then it's going to change along the time. And the current exploration rate is the epsilon start that we defined up there. Start time, we just keep track of time here, and we enter the episode for each episode in the range of number of maximum episodes. We get the current observation by resetting the environment, and the dawn is set to false, and score and time step are also initially 0. Then until it's not done, we start to go explore and exploit through the episode by taking an action which select action function were defined, given the current exploration rate, current observation, and DQ agent. Then the next observation, reward, done, and info comes from taking the action we selected for the next state, for the next movement. So it gives us the next observation, and then also reward and done and info. This observation has been reshaped, kind of flattened, I believe. Yes. I think the main reason is that the observation output is usually, we sometimes say observation next of 0, but whatever. So its dimension, it it takes care of the dimensionality to better use it. And then we need to define what experience is. So if we remember from the memory, what we were keeping in the memory is our experience, that we want to add it, append it memory by it. So it had current observation, action, reward, observation, next, and down flag. Then we are done with this time step. So imagine that the time step has finished here, so we want to define whatever has happened here that was considered for future. From now on, it's current situation. So current observation will become our next observation, because we are moving to the next time step. The score is added by reward, and time step is added by 1. And this loop keeps going until it gets done here. And then we come out of the loop, and we want to print some information like what's the exploration rate, and also at the end of the episode we want to change the exploration rate. So we want to multiply it by epsilon decay rate, but we want to make sure that this doesn't get any smaller than the epsilon minimum, so we take the maximum value of these two. Then we also print some logs, like what's the score at the end of the episode, and what are the and also we add the score to the list of the collected rewards for as a history. And also we check if we reach the batch size that we expect, if the memory has enough in it, enough equals to the batch size. We replay to update the DQ agent by giving it the memory, DQ agent, target agent, batch size, and gamma. So now here are the counter updates, and then we need to copy the weights of DQN agent to target agent every target update step. So we set if um, update counter as like target updates tapes. Let me see where we define this one. Target update steps. I'm not finding it. Yeah, so if I want to see, we have defined this previously. I believe that there are a number of steps that after that we want to update the targets. So if this is like the remainder of this um, current update counter has passed one entire update number of update states, it updates the weights by setting the weights to the DQN agent that get weights. And then we close the environment, and then we check how much time it took from us. So here you can see that the time is moving forward, and this is just total training time is like 850 seconds. And here we want to keep track of how the reward has changed along the time for different episodes. Um, so in the x-axis we have number of episodes, and in the y-axis we have reward per episode. And we see that in the beginning it's kind of fluctuating, it's not perfect, but it's keeps increasing until it keeps increasing to very high points. But still, as you can also see in the video up there, maybe it's not perfect, it's like kind of fluctuates very fast. But it works, it looks like it works, but it can get better too. So we're plotting, what we plot here is the reward collected, that we were adding the reward to it in a list that I said we can keep track of it later to see how it works. Now we want to render the, oh, I hope it works here, because yeah, it didn't work. So the next thing is to record what happens to be able to render it in a kind of video that we can see, but it takes 800 seconds, 850 seconds, so it doesn't worth rerunning. But it should act something like this guy in here. This one maybe a little bit more fluctuating, but it looks like it doesn't fall. So thank you.